So today's lecture is going to be pretty short, sweet. It's on cation and anion exchange capacity. If you've had me in class, we kind of touched on this a little bit. And remember, we watched that video. And so if you aren't in the class and you're taking this from the outside, at the end of this presentation, there's a video that you can watch that kind of sums everything up and kind of gives this big, broad overview of what I talked about today. It kind of just squeezes that in. But when we're talking about adsorption of cations, remember cations being positive and anions being negative. And so there are two types of adsorption that we can have. Remember, adsorption being the piece of tape where it can desorb and then adsorb back again. We have these outer sphere complexes and these inner sphere complexes. And so the biggest difference between these two is that for outer sphere complexes, there is a water molecule that surrounds the cation, and for inner sphere complexes, there is no water molecule. So outer sphere is easily exchanged because of that water molecule. There's this thin layer that is kind of deadening some of that charge, whereas for inner sphere complex, it's a direct covalent bond between, and we'll see this in the next slide. So here we have our outer sphere complex with this water molecule. We have water molecule surrounding this calcium 2+ and forms an electrostatic bond with this hydroxylated edge of this tetrahedral layer. This is actually in gibbsite, but it would be the same if it were in kaolinite. And so because there's a hydrogen bond here, there's only one of them. So if we have a lot of hydrogen bonding, we have a very strong attraction, like in our kaolinites. Like we have enough bonds in our kaolinites that there's no shrinking and swelling because the charge is so tight in there. Here we only have one or two hydrogen bonds, and it doesn't take as much force to desorb that, as indicated by this line here. However, if we were to look at phosphate, we do not have any water molecules surrounding it, and therefore it forms a direct covalent bond with the oxygens in that tetrahedral layer. So this is just an electrostatic kind of, in the video it'll talk about where you rub a balloon against your head and stick it against the wall. You all ever did that as a kid? Eventually that charge is eventually it wears off and the balloon falls. Here it's like the tape where you have these covalent bonds. They're now sharing electrons and they don't want to let go of each other because they're finally stable. So outer sphere, water molecule; inner sphere, no water molecule. So look at just some extra information about the difference between outer sphere adsorption. No direct chemical bonding. And then this is almost from the beginning of the lecture that we did, where cations are positively charged, adsorb to a negatively charged surface, and anions are negatively charged, attracted to positive charges in surface. A few things that are going to affect this adsorption is the type of surface charge, which is going to possibly be directly related to pH. Also some isomorphic substitution depending on which ion is in the middle. The valence of the ion, whether it's calcium 2+ or whether it's K+. So calcium being 2+, having a greater valence charge, is going to be adsorbed to that particle greater than K+, it only has a +1. And then the types and the concentration are going to have an effect too. It's reversible, and this is what we primarily consider our CEC. We can have some attachment to oxides in organic matter. And then there's this diffuse double layer that I talked about in the very first lecture, where we have all of these ions that are together, and that's going to depend on how strongly they're attracted to that hydroxylated surface of that tetrahedral layer, which goes back to the type of surface charge. Next, we have this inner sphere. Again, the covalent bonding. That is, they're locked together. I consider those like a chain. You might hear it called chemisorption or specific adsorption if you move into soil chemistry, may or may not. And so inner sphere complexation is going to be dealing with our anions because they'll have a negative charge on it based on these oxygens that are available. Right? So if we have calcium, we don't have the oxygen as part of the molecule that makes the overall molecule up. But in our sulfates and nitrates and phosphates, all our eights and our ites are going to, you can pretty much figure that they're going to have some inner sphere adsorption. And they're dependent upon the solubility of the ion. And so phosphorus is not very soluble, but nitrate is. And so nitrate is very soluble in water, so it will be easily desorbed off of this inner sphere, from this inner sphere complex, because it's soluble in water. So the water can form some attraction to this nitrate molecule and cause some distance between the outer layer of that tetrahedral and the molecule. It's not that nitrate has water, but water comes in between there and kind of pushes that away from that outer layer. The surface properties, and then also our pH dependent charge. And do y'all remember what the three sources of pH dependent charge were? Functional groups of organic matter, aluminum and iron oxides, and broken edges of clays. We have some simple cation exchange reactions. It's basically a 1-for-1, where we would have a positive 1 charge and a positive 1 charge. Sodium on the clay colloid, hydrogen in solution, and those two will just change for each other. Next, we have charge equivalence, where we would require 2 hydrogens to dissociate 1 calcium. So this is where charge comes in on how well these cations and anions are adsorbed to the soil colloid. We have this ratio law. We see here that the ratio between calcium and magnesium is a 4-to-1. 4 on the colloid, 1 in the solution. And then we find that we have 4 on the colloid and 1 on the colloid. 1 in solution, 4 in solution. Much of our fertilizers are applied as salts because we need some water to dissociate those two, the two molecules that make up the salt, so that water adsorbs to sodium and forms that water molecule around it, or to calcium and has that water molecule like we saw in the example. So in the top 50 centimeters, we can have about 30,000 kilograms of exchangeable cations. You're typically going to find most of them as calcium because we apply a lot of lime. Next, followed by magnesium, potassium, and sodium. And so as we finish out this lecture, and we'll be moving into next lecture with our going over pH and some liming calculations. It's important to understand that as pH decreases, our hydrogen concentration is going to increase, along with our aluminum. But when we increase the pH, so when we apply lime, maybe like a calcium magnesium carbonate, calcium, magnesium, are going to be released into the soil, and that is going to have some other reaction with this aluminum that is going to neutralize some of the active acidity. And so that's the purpose of applying lime. So that we can get this charge, we would need 3 moles of calcium to displace 2 moles of aluminum. But if we applied calcium, with 1 mole of calcium, we could replace 2 moles of hydrogen. Based on the charge. Based on the charge. So we went over this also in the first lecture as an introduction. This is the lyotropic series, and so we see that as our charge decreases, the adsorption to those soil colloids decrease. Our +1s are not held so tightly. Our aluminum is held very tightly. And so since our outer sphere complexes have that water surrounding them, it is going to, how tightly they're held to the soil is going to be based on A, the charge, and then B, the radius of the water. And so you can think about it like a hula hoop. So aluminum has a great charge with a very small hydrated radius. And so it's attached closer. It's attached more tightly because the charge does not have as much water to overcome. The distance between the center of the aluminum charge and the center of the oxygen on the tetrahedral is very close. So they're held very easily. But if we had sodium, which is a +1 that has a very large hydrated radius, you can think about this like a very big hula hoop, and the charge between the center of the sodium ion and this large radius that has a lot of water in between it, the sodium can't really adsorb over, so it's just kind of attracted, sort of almost barely touching the outer edge of that clay layer. Aluminum, high charge, low radius, held very tightly. Sodium, low charge, high radius, not held as tightly. It's about the distance between the charge attraction. Then we have complementary ions, and that's saying that at some point there needs to be some balance in here between what is on the soil colloid and what is in the soil solution. That's all that really is saying. So when we take our soil samples, we send them off to the lab, and they give us a number back, and they tell us what our CEC is. What they've done is they've measured the effective CEC, the soil as it is. They add water, they measure it just like it is, like without any changes. And then they'll do the buffer CEC. And remember, we've talked about pH dependent charge several times. And so as our pH increases, as our pH becomes more alkaline, our CEC improves based on that pH dependent charge. So they'll raise it to 7 or 8, make sure that they've dissociated all of those hydrogens from those functional groups of organic matter, and now we know that we have an extra set of charges out there. And so that's why we apply lime, is so that we can increase our CEC. In the video, it talks about the small cup versus the big cup. And so something like kaolinite, which has a very low CEC, if it were acidic, it might have a CEC of 4 or 5. But if we added lime and made it more alkaline, we might get 12. CEC of 12. So it's important to remember that acidic soils have a lower CEC. Alkaline soils are likely to have a greater CEC because of the pH dependent charge. That's why I've gone over it so many times. It's because this is where you're going to gain a little bit of extra. What's most important here, one of the things that we're going to do today is calculate we're going to calculate CEC and our percent base saturation. And the thing is that CEC is going to vary with soils. And CEC might vary between here and the hallway out there. So it's an average at best, because soils are variable, like they form differently. So back to our inner-sphere complexes. This is also the lyotropic series for our anions, again the charge. So we have this extra charge here, and we also have another hydrogen that's adding to some of this charge, followed by sulfate, nitrate, and chlorine are going to be the same because they only have a -1 charge. This is going to be important in our highly weathered acid soils. So our oxisols, ultisols, those red clays, there aren't any other elements, cations that are held in there. Everything's been weathered away. Pretty much what's left is aluminum and iron oxides. Hey, guess what? pH dependent charge again. But in reverse. So as we okay, acidic soils, lower CEC. And if our CEC is low, what would you expect the anion exchange capacity to be? High, right? Because this is a balance. And so if we have alkaline soils with a high CEC or greater CEC, what would you expect the anion exchange capacity to be? Low, correct. In our acid soils, you would expect the AEC to be high, which means we can hold on to more anions. So the way that they kind of measure this and the way that we look at it, remember we talked about that as our pH decreases, we increase the acidic cations, hydrogen and aluminum, and our base cations are going to be what we're trying to hold on to that our plants are going to use. And that's going to be dependent on what soil type is there, what, whether it's smectite or vermiculite, how they measure the CEC, and then finally how they determine, like the percent base saturation or cation saturation. So the way they measure this is we're going to sum all the base cations. After they've exchanged them off the exchange sites, we're about to go over a demonstration of this. It's important to know is that this is reported as centimoles of charge per kilogram of soil. That's the unit. So here's the soil sample you sent in. They will flood it with an ammonium solution that has a strong concentration, strong ion concentration, that will overpower our calciums, our aluminums, our magnesiums, will overpower, and they will be flushed out. They will measure this solution to determine what cations are available and at what concentrations. Next, they'll come back with a potassium solution to exchange the sodium off, the ammonium, and then they'll measure the ammonium as well. It's kind of like a mass balance. What was there before, what was there after, and they'll determine how much might be left here. So now we're going to calculate our CEC and percent base saturation. It's pretty much just simple addition. You will be adding across. The first thing we are going to do is add up our total acids. That's part of the sheet too. Yeah, you're going to do it on the sheet. Yeah. Right here. Let's just do number 1.
Oh, so we just add those.
Yeah, you're adding and putting 33 plus 13 is
46.
46. So 46 would go here. We would calculate that all the way down. Good numbers?
Good.
Okay, cool. Simple addition. I like to keep it very simple. All my math is simple, and I'll walk you through it very easily. Next, we're going to calculate the total bases. Which are calcium, magnesium, potassium, ammonium, and sodium. You should be calculating these for those of you watching. Go ahead and calculate those all the way down. Done? 110, 73, 50, 23, 14, and 9. Cool, right? Easy math. Next, we're going to sum both of those. We'll sum total acids plus total bases. One 156, 123, 106, 73, 49, 36. Cool. What's that?
39.
39, I'm sorry. 39. Next. That's our total CEC. Next, we're going to divide the bases by the total CEC, and this will give us percent base saturation. (110 by 156).
Good decimal.
2. There we go, Jacob. Just for the sake of saving time, so we're not watching the video this forever long, when we know that what we're going to do is just multiply that or divide that all the way down. And so these are, this may be an O horizon, maybe an A horizon, AP, B, BT, BW, whichever, right? But we're increasing depth, top, bottom. And you can see that as our depth increases, our base saturation is going to decrease. So not only is this going to influence the nutrients that we apply to our soil, but they're also going to have some impact on some other things like pesticide applications, where we have some adsorption and some complexation and partitioning, which is more soil chemistry and whatnot. But just to understand that as our pH increases, our CEC will increase. And as our pH decreases, our AEC will increase. So important to understand what chemicals you might be putting out and how the CEC and the AEC might affect the efficacy of those chemicals. So let's take a look here, just as an example. Many of us are familiar with BT. It is something that is used in corn for the corn borer. And so what they decided, what this experiment is showing is that they added the same amount of BT to montmorillonite, which is a 2-to-1 clay, and then also kaolinite, which is a 1-to-1 clay. So which one would have the higher CEC?
Sorry, I'm still writing.
Okay. BT is just a toxin that they added to the soil.
Okay.
Montmorillonite and kaolinite, which one has a greater CEC? Correct, montmorillonite. So it's going to adsorb more of what was applied. So montmorillonite adsorbed more of this toxin compared to if we added this to a kaolinite. Just a demonstration to show you that greater CEC will have greater adsorption of cations. All right, this is a picture of a wheat field in Africa. We notice right here that the sandy A horizon has a low CEC of about 4 centimoles, but underneath it, the clay has a CEC of about 12 centimoles. So they applied this herbicide to this field and didn't quite work right here. So you go to apply this herbicide and you go, how come it didn't work? Well, first thing, maybe this is a resistant species of this weed, right? It's possible that we could be getting some resistance. It's possible. But next, what they did is, what happened is some of the clay soil was brought up in this location, in these locations. And so now here the CEC is 4. Here the CEC is 12. So much like the same example before, this may be a kaolinite, and we might have had smectite here. Smectite being a 2-to-1 has a greater CEC. It adsorbed some of that herbicide, and it didn't act. It was not activated because it was so tightly bound to the soil that it didn't work. And then finally, here is another example. Atrazine is something. Atrazine and metolachlor are common herbicides used in grasses, and we have these partitioning coefficients, and also our organic carbon, and our organic matter created a strong adsorption for this particular secondary molecule of atrazine. And so typically what we'll do is we'll apply it as atrazine, expecting it to degrade into some other compound that might be the active compound that the plant can take up and ingest, absorb with a B, that ends up killing the plant. And so if hydroxyatrazine was one of those chemicals, the secondary compound, and the plant can't take it up because it's held so strongly to the soil, that's what happened. The chemical didn't work. Still the same chemical, it's just adsorbed. It's locked into that CEC. Also that we have a lot of organic carbon. So now maybe this is soil organic matter, pH dependent charge, functional groups of organic matter, and if this were a positively charged cation, it's held to that little extra functional group of organic matter that now has that negative charge on there. And so what happened is it adsorbed everything to the soil and the plant did not take it up. So something to think about when we're thinking about CEC, adsorption and desorption, and how those things are going to come on and off of our exchange sites. And again, this is the video. If you weren't in, we're not going to watch it, but if you weren't in soils class, this is going to basically explain in a better way, a little bit more lively and kind of, I liked it. A student gave me this and I watched it and I went, that's everything I've been trying to tell you. So this is a really good video to watch to kind of gather some more, to kind of conceptualize what that looks like actually in the field and how that applies to agriculture. All right? I think that is it. We'll be talking about soil pH and liming. We'll pick up kind of along this cation and anion exchange as we move into soil liming for next class period. Y'all have a good weekend. See y'all next Friday.